This video covers Unit 4, Lesson 1. We are talking about graphs of inverse trig functions today. Before we start talking about the trig functions themselves, I want to revisit a concept that we talked about in Unit 3, where we discussed functions and their inverses, and we were looking at the graphs of functions as one way to determine whether or not the inverse of that function would also be a function as well. So when we look at d inverse of x, we know that its inverse would not be a function because d of x does not pass the horizontal line test. Or similarly, if we thought about reflecting and drawing the curve, so reflecting it over the line y equals x, then we know that the inverse, okay, so this would be d inverse, does not pass the vertical line test. So we know, again, d inverse is not a function. When we look at this next one, this cubic function, because it passes the horizontal line test, even when we were to reflect it, we would see that, yes, its inverse is a function. So when we run into a function like d of x whose inverse will not be a function, we say that that relationship is not one-to-one. So a function, something can be a function without being one-to-one. We know that a function is a relation where each input has at most one output. If it's one-to-one, we add to that story a little bit. So we have this definition: a relation is one-to-one if each input has at most one output. So that's our function definition, but then we add on to it and say, and each output has at most one input. So this again assures that it's going to pass both the vertical and horizontal line tests. When a function is not one-to-one, again like d of x, then we can do something called restricting its domain. We can take the domain of that original function and restrict it, so basically chop part of it off so that the inverse will be a function. So let's revisit our graphs here, and we're going to focus just on the one that had the relation that was not a function, or sorry, the inverse that was not a function. If we look at this graph, basically just by taking part of it, in this case exactly half of it, if we just restrict the domain to be 0 to infinity, then when we find the inverse, its inverse will be a function. So we're just going to kind of ignore this part of it. Let's take a look at the graphs at the bottom of the page again. So we know that this would be the graph of the inverse of d of x without restricting the domain. I want you to think about that piece that we drew if we just focused on this part of it. When we reflect that over the line y equals x, then we would just have this piece here, and we would be ignoring this half of it, and that's what this graph shows. We just have this half, and that part is a function. It passes the vertical line test. It has every input, only one output. So if we were to algebraically solve for the equation of the inverse originally, we would get plus or minus square root of x minus 3, and that would give us this entire sideways parabola, and again, not a function. So by restricting it and just having this piece, the new equation d inverse of x equals just the positive square root of x minus 3. This is a function, and we are happy. There are all kinds of functions that are not one-to-one, and so we have to do this restricting of the domain in order to make their inverse a function. Even functions like the parabola we just saw are just one example. Another example are trig functions. So when we look at the graph of sine of x, remember sine of x without any transformations starts on the midline, ends on the midline, which in this case is the x-axis. Starts moving up to 1, down to -1, and then 1 complete period is 2 pi. Even if we were just to look at one period of our sine curve, we can tell that it is not one-to-one because it wouldn't pass the horizontal line test. So we need to do some restricting here. When mathematicians decide what kind of restrictions they're going to make, they're looking for what section of the graph, section or sections, will the function be completely increasing or completely decreasing on. We don't want it to have any parts that are both increasing and decreasing, because that's what makes it not pass the horizontal line test. So there are several sections of the graph that these mathematicians could have taken in order to do that. Before I talk about what they chose, I just want to show you what the graph of the inverse would look like without the restrictions. So here we go. All I did was take a bunch of the ordered pairs like 0, 0 and pi over 2, 1, and flip them around. So 0, 0 remains, and then I have 1 pi over 2 as one of my ordered pairs. I did that for the rest of them, and we can see this inverse graph is not a function. So when we are looking at restricting the domain of the original graph, if we grab this part of it right here, so from negative pi over 2 to pi over 2, that entire region is increasing the entire time. It also grabs all of the possible y values. So we want to grab as much of the range as possible, all of the range, truly. So if I transfer that over to what is on our inverse graph, we can see that that passes the vertical line test and therefore is a function. So we're basically just taking a snapshot of the original sine graph, and then that gives us the, reflecting it over y equals x gives us the inverse sine graph. So by restricting the domain from negative pi over 2 to pi over 2, we get a range of sine inverse of negative pi over 2 to pi over 2. Remember, that's how inverses work. The domain becomes the range. The range here, negative 1 to 1, becomes the domain of this function, negative 1 to 1. We'll summarize all of those pieces in a moment here. So let's move on to talking about the cosine graph. So when we're looking at cosine, we need to look at a different region from sine, because negative pi over 2 to pi over 2 has a region that's both increasing and then decreasing, and so doesn't pass the horizontal line test. So we need to pick just a different region that is either completely increasing or completely decreasing. The region that the math gods chose is this one. So we go from 0 to pi so that it's completely decreasing. It doesn't really matter if it's increasing or decreasing. All we care about is, again, grabbing the entire range and making sure that the inverse will be a function. The reason I think that mathematicians chose this section rather than, say, a section over here is because it kept the values more in the positive region and close to 0. So once we construct our inverse graph by just flipping some ordered pairs, and then we look at that same region from 0 to pi, now on the y-axis instead of the x-axis, we can see that restricting the domain of the original function from 0 to pi ensures that the cosine inverse graph is a function, and it will have a range from 0 to pi. So we haven't touched on the tangent graph in class yet, so I want to talk you through how it's constructed. If we just start with plugging in some ordered pairs, plugging in some angle values for tangent, like an angle of 0, we know that the ordered pair there is 1, 0, and so tangent's 0 over 1, which is 0. So we have the ordered pair 0, 0 on our graph. If we think about pi over 4, at pi over 4, I know it's not listed on the x-axis, but you know it's halfway between 0 and pi over 2. At pi over 4, tangent of pi over 4 is 1, because it's root 2 over 2 over root 2 over 2. So we have the ordered pair 1. And then similarly at negative pi over 4, we have negative 1. Once we get to pi over 2, because the ordered pair on the unit circle at pi over 2 is 0, 1, The tangent at pi over 2 is 1 over 0, which is undefined, which is why we have an asymptote here. Same story at 3 pi over 2. We have negative 1 over 0. So all of the pi over 2's on our tangent graphs have asymptotes, and then we have almost a cubic looking function in between the asymptotes. And then after doing the reflection, you can see what the tangent inverse graph would look like without any restrictions. So it's usually pretty easy to see what section we could choose that is either always increasing or decreasing. So this region of the tangent graph is what is selected for the restriction. So we are looking at negative pi over 2 to pi over 2. That grabs all the values of the range. The range is negative infinity to infinity, so that grabs all of it, and then it doesn't have any repeats, so to speak. We do have the parentheses around these instead of the brackets because at pi over 2 and negative pi over 2, the function is undefined. So we had brackets with the sine function. Sine is never undefined. We had brackets with the cosine function because it also is not undefined. But with tangent, we have the parentheses because of those asymptotes. It's important when we're working with trig functions and their inverses that you make sure you are clear on what exactly the input and output values represent. So we've worked a lot with our regular trig functions, and we know that we input angles. Those angles could be in radians or degrees, and we output ratios. So we're talking about the side lengths of the triangles that are constructed around the unit circle. Because the inverse switches the relationship between the domain and range, or the inputs and the outputs, that means we will input ratios into our inverse trig functions, and the outputs, or the answers, will be angles. So that's going to be an important distinction once we actually start practicing some problems. On the rest of this page, we are just going to summarize what we did with those graphs from before. So starting with just talking about our regular functions, sine, cosine, and tangent, so not the inverses yet. When we restrict their domains, we restrict sine from negative pi over 2 to pi over 2, cosine from 0 to pi, tangent from negative pi over 2 to pi over 2, but with the parentheses again instead of the brackets. You can see in green here, I also listed what those values would be in degrees. I focused mostly on radians for the graphs because we graphed always in radians, not degrees, but we can talk about their degree equivalents as well. Then when we talk about the range of those graphs, there's no restricting of the ranges or anything like that. It's just that the range of sine, we know, goes from negative 1 to 1, and cosine also from negative 1 to 1. And now that you've seen the tangent graph, you can see that its range goes from negative infinity to infinity. In the next row, we're looking at the inverse graphs. So all we're doing is taking the restricted domains from above and the ranges and flipping them around. So now the domain of sine inverse and cosine inverse is negative 1 to 1. The domain of tangent inverse is negative infinity to infinity. And what that means is when we're working with these inverse functions, into the x value, you can input for sine inverse only something between negative 1 and 1. Otherwise, it's going to be undefined. Similar situation for cosine, and you can really put in anything for tangent. Then the types of things you're going to get out once you input one of those values are things between, for sine inverse, negative pi over 2 and pi over 2 if we're in radians, negative 90 to 90 if we're in degrees, and then you can see how that transfers over into those other functions. I want to focus for a minute on this notation here. So sine inverse, with that, it looks kind of like a negative 1 exponent. Sine inverse of x could also be expressed as arc sine of x, so just the ARC in front, and then it's similar for the others as well. So we can say cosine inverse of x or arc cosine. They mean the same. Now, the last thing on this page are just some graphs of the unit circle for you, and I want to highlight where these ranges fall. So for sine, it's negative pi over 2 to pi over 2. I know what's listed here is 3 pi over 2.
but we're going to think about it as that negative to the positive. For cosine, it's here to here, so 0 to pi. And for tangent, I'm going to put open circles from negative pi over 2 to pi over 2, because it can't actually equal those values, but it does go right up towards them. The last page of your notes for this lesson, we're finally at a point where we're going to practice some problems. And we'll start by thinking about these in terms of degrees, just because I know most of you are a little bit more comfortable with degrees than you are radians. So when we're looking at sine inverse of root 2 over 2, remember that input, root 2 over 2, is a ratio, and so we are looking for an output that is an angle. So you're basically asking yourself, what angle would produce a sine value of root 2 over 2? And remember, you're only looking from negative pi over 2 to pi over 2, or I guess negative 90 to positive 90 in this case. So we know that root 2 over 2 is positive, so if we're focused just on these two quadrants, we must be in the first quadrant, because the fourth quadrant produces negative sign results. And then you just have to think, well, what angle gives us root 2 over 2 for sine? And that is 45 degrees. Done. On to the next one, arc tangent of 0. So remember, that's just another way of saying tangent inverse. Arc tangent of 0, we're looking in the same region. We're looking for tangent values that, or an angle where the tangent value would give us 0. So zeros occur on the axes. So if you look at this one in the middle right here with that ordered pair of 1, 0, because tangent is sine over cosine, we would have 0 over 1, which is 0, so the angle is 0 degrees. In the next one, I'm asking you about secant inverse of 2 root 3 over 3. And we didn't talk about the inverse of secant, cosecant, or cotangent. And that's because we don't really need to talk about those graphs, because we can just turn these back into cosine, sine, and tangent problems. So instead of asking ourselves what secant inverse of 2 root 3 over 3 is, I can restate the problem as cosine inverse of the reciprocal, since secant and cosine are reciprocals of one another. Now, if you rationalize this, you will rationalize and simplify. You will get to cosine inverse of root 3 over 2. And then you're going to approach it the same way we did for A and B. So remember, cosine inverse is a little different. For that one, we're looking at the top half of our graph from 0 to 180. Cosine, the angle that would produce a positive root 3 over 2 would have to be in the first quadrant, because in the second quadrant, cosines are negatives. And then the cosine's the x value, so we're looking for the x value that's longer, so it would have to be the angle that's closer to the x-axis. So we would get 30 degrees. One more in degrees before we switch to radians, and this is a composition, so it's asking us to take sine inverse of sine of 150 degrees. So you know how to work with compositions. We always start from the inside out. Notice that the very inside is the regular sine, not sine inverse. So sine of 150 degrees, you guys know what that is. We could have answered that from unit 1. So if we go to 150, it's closer to the x-axis, and so the y value is going to be the smaller one, so we will have 1/2. And then we want to take sine inverse of 1/2. So treat this like a new problem. Start over. And when you're looking at sine inverse of 1/2, you are looking from negative 90 to 90. Same story as the others in that you want to think positive and negative. I know I have to be in the first quadrant because the 1/2 is positive. And sine is going to be 1/2. The y value will be 1/2 closest to the x-axis. So we will have 30 degrees. as our final answer. Now, I just want to mention one thing, and we'll discuss it more in class as we continue throughout the unit. We just finished a unit on inverses, and we talked about how taking sine inverse and sine, or f inverse and f, they kind of cancel each other out, and then you're just left with this value. But you guys know that 150 is not equal to 30 degrees. When there's been a restriction on the domain, that rule no longer necessarily applies. So again, more on that later. All right, let's switch gears here and do some radians in the other column. So arc cosine of 1, looking at 0 to pi. So looking at where from 0 to pi is the cosine value positive 1. So the x value positive 1. That would be at a radian measure of 0. Next, tan inverse of 1. So tangent, looking from negative pi over 2 to pi over 2. We know we have negative values in the fourth quadrant, so we are working in the first quadrant. In the first quadrant, the angle that gives a tangent of 1 is pi over 4. And let's do a sine inverse. So sine inverse, negative pi over 2 to pi over 2. This is sine inverse of negative 1/2. So finally we're dealing with some negative values here. Because everything is positive in the first quadrant, I know that I need to be in the fourth quadrant. Thinking about a y value of negative 1/2, so the short one, I know that I'm talking about the angle closer to the x-axis opposed to the y-axis. So those are the pi over 6's. Now, unlike some of the problems we did in Unit 1, where we usually just talked about one positive revolution of the unit circle, so 0 to 2 pi, unlike that, where we might be thinking the answer is 11 pi over 6, you have to make sure that your answer falls between negative pi over 2 and pi over 2. So your answer in this case would be negative pi over 6, because 11 pi over 6 doesn't fall in that range. Okay, on to cosine inverse of negative 1/2. Cosine, top half of the graph, 0 to pi. Again, first quadrant is a no-go because everything's positive. Cosine inverse of negative 1/2. So the x value is the short side, which means we're going to be closer to the y-axis than the x-axis, and those are the pi over 3's. Cosine inverse from 0 to pi doesn't ever give us any negative values out, where sine inverse and tangent inverse do. So we can just be thinking about our positive revolution around the circle. So this answer is 2 pi over 3. And then the last one on this page, another composition. So working from the inside, now on the inside we have the sine inverse. I know it says arc sine, but we know that's the same thing. So sine inverse of 1/2, we will be in the first quadrant because that's where things are positive. Sine is 1/2, meaning we are going to be, the short side is the y, so that's going to be pi over 6. And then we have cosine of pi over 6. And so looking at that same triangle, cosine of pi over 6 is root 3 over 2, and that is your final answer. On to our last set of problems. We are going to pick up our calculators in order to do these, but I'd like you to think about what kind of answer you can expect before you type it into your calculator. It's just going to be good practice for your conceptual understanding of inverse functions. So again, we're going to start in degrees, and when we're thinking about these problems, sine inverse of 1/3, hopefully you can see why we're going to pick up our calculators here. 1/3 is not a unit circle value, so when it's not on the unit circle, we need some other tools in order to help us. So just as we were doing before, I want you to think about the restricted domain of sine, the range of sine inverse. And think about the quadrants. So 1/3 is a positive number, so we know that our answer should be in the first quadrant. If you want to push yourself even a little bit more, try to compare 1/3 to a unit circle value that you know. So 1/3 is a little bit smaller than 1/2. We know that a sine value of 1/2 would be an angle that is close to 30 degrees. So 1/3 would bring that triangle side a little bit lower. So we would expect an answer that's less than 30 degrees. So you're going to pick up your calculators and you're going to make sure you are in degree mode. So go into your mode function, make sure it's on degrees. And then you're going to type in sine inverse, which means you're going to have to use the second button on your calculator. So sine inverse is right above sine. So you're going to press second sine, and you should see sine -1 show up on your screen. And then type in 1 divided by 3, hit enter, and 19, we'll just round to the nearest tens, 19.5 degrees comes up as our answer. So again, it's in the first quadrant, less than 30 degrees. On to the next one for cosine. Cosine's range is going to, cosine inverse range is going to be from 0 to 180 degrees. Because 2/5 is positive, we would expect a first quadrant answer. You're not going to find arc cosine on your calculators, at least I don't think so. Most of you probably have the TI 84 or 83, so you'll just see cosine inverse. So that's what you're going to type in. So second cosine, 2 divided by 5, we get 66.4, and that is consistent with our suspicion that it would be a first quadrant angle. On to the next one. You can just type this entire thing into your calculator at once, but before we do that, let's think about that inside piece. We know that we will have tangent inverse of -0.6, so we would expect, in order to get a negative value, we would expect something in the fourth quadrant. But remember, that's going to be a negative angle. You're not thinking about it between 270 and 360. You're thinking about it between -90 and 0. So if I type in tangent inverse of -0.6, I get about -31 degrees. So I know I'm thinking about it the right way. Then I need to take tangent of the -31 degrees, and I get -0.6. So this is a case where the tangent and the tangent inverse did just kind of cancel each other out, and we got back to our starting point. Like I said, sometimes that doesn't happen when we restrict the domains, but sometimes it does, and in this case it did. On to radians. So now pick up your calculator, change the mode into radian mode, then get back to your home screen. Thinking about this before we do it, cosine inverse, so we're looking at 0 to pi for our potential answers. Cosine inverse of -√5/2, not going to be in the first quadrant because things are positive there, so I'm expecting an answer between pi/2 and pi. When you're typing in the -√5/2, make sure just the just the 5 is underneath the square root. And what's going to happen, if you're doing this with me, and I hope you are, is that you are going to get an error on your calculator. And a lot of times when our calculator gives us an error, it will tell us what the error is. So my calculator right now says error domain. So there was a problem with the domain. If you figure out just what the decimal equivalent of -√5/2 is, you will see that that value is about 1.1 or -1.1. And if you flip back one page in our notes and take a look at the domain of cosine inverse, you will see that the domain of cosine inverse is from -1 to 1. And -1.1 falls outside of those values. So because -1.1 is outside the domain, our answer is actually that this one is undefined. So similar to can't take the log of a negative, you can't take cosine inverse of a value that's less than -1 or greater than +1. And the same thing is true for sine, since its domain, sine inverse, because its domain is -1 to 1. So, kind of a tricky one there, but we'll see more of those pop up. On to D, we have sine inverse, arc sine, right? Because it's a negative value, we know that we're going to be in the fourth quadrant, so we're going to expect our answer to be between -pi/2 and 0. That means when I type this in, I should see a negative value show up on my screen. And I got -0.41. Usually with radians, we'll round to the nearest hundredths. Degrees, we keep to the nearest tenths. All right, last one. We're almost there. So we have cosine inverse of 0.25 on the inside. Cosine goes from 0 to pi, so we will be in the first quadrant. So when I do cosine inverse of 0.25, I see an answer of 1.32. Now, you might be saying, okay, how do I know that's in the first quadrant? 1.32. If you figure out what pi/2 is, pi/2 is about 1.57. That can help you determine if the quadrant was correct. So 1.32 is less than that, less than 1.57, so you know that that is a first quadrant angle. And then take the sine of that value, and you get about 0.97. So, on your assignment, if you have any that you're being asked to evaluate with the calculator, I'm still going to expect that I see these diagrams drawn so that I can see you are thinking about it rather than just typing it in. That's all for this lesson. More good stuff to come in lesson 2. We'll solve more complicated trig equations.